We previously looked at the conservation of momentum, so now it's time to look at the conservation of energy. Don't forget that we explored several different forms of energy, everything from electrical energy and chemical energy. What we're going to deal mostly here with is mechanical energy. But the conservation of energy applies to all forms of energy. And basically, the conservation of energy law just says that the energy, and they talk about a closed system, but the total energy never changes. It might be converted. It might be converted from, say, um, mechanical energy to sound energy. As I clap my hands, maybe that's chemical energy becoming sound energy. So it just changes its form. So in the basics, we've got the total energy in a system before something happens will equal the total energy in a system after something happens. And once again, I'm going to use this. I'm just going to say E total before equals the E total after, and using that little prime system there to indicate the after. Some people like getting into big formulas, so we could call it the energy kinetic, the energy potential, the energy elastic, and any other energies that you want to put in there would equal the energy kinetic after, plus the energy potential after, plus the energy elastic. I'll put capital E this time, after. And remember that some people use the format of kinetic energy, potential energy, and elastic energy. It's staying the same thing. But just so you can see it, kinetic energy, potential energy, and elastic energy. We're just adding up all the energies before and making sure that they equal something after. Let's now try a few examples and see if we can solve this. So here we have a boulder sitting on a cliff. Now, how did that ever get there? Who knows? But let's say, for instance, wartime. You'd have a ship down here, and they would shoot cannonballs and stuff at you, and it would be quite effective in wartime. Let's just clean up my diagram here a little bit. But I've got this big rock here, and it's got a mass of 5 kilograms. So what I'm going to do, and I got a height here. I got a height of 30 meters. Okay. So let's calculate our types of energy. Okay. So how about our elastic energy? Well, there's no elasticity going on here. We haven't shot a bow and arrow or jumped off a diving board. So the elastic energy is 0. We do have some potential energy, and the potential energy here is due to gravity, right? It's 30 meters high. So this is going to be the mass times gravity times height, which is equal to, let's see, the mass of 5 kilograms and the height 9.81, gravity, 9.81 meters per second squared, and the height of 30 meters. So that's 150 times 10, roughly. I'll just be under 1500. How about 1471.5 joules of potential energy? And what about our kinetic energy? Our kinetic energy here is 0. It's not moving. It's just sitting there on the edge. And maybe I should move it a little closer to the edge here. There, it's just balanced right on the edge. Okay. So what is our total energy at the top? Our, I'll put E total at the top. And the total energy at the top, well, we're going to add 0 plus 1471. So we've got that much total energy at the top, way up here. Okay. Well, what about at the bottom? This thing, we know that this thing is going to get a nudge, and in a moment, it's going to be traveling down, and it's going to land here. Okay. So what I want to know is, the energy down there. Well, the total energy at the bottom, and we're talking the bottom, just that split second before it hits the bottom, the total energy at the bottom is going to be the same as the total energy of the system, okay? And this is the conservation law right here. This equals that. Okay. So I'll say with the black color here. So what is our elastic energy? Well, our elastic energy is still 0. It didn't hit a spring or something at the bottom, so it's 0. What about our potential energy? Well, our potential energy, now it's still this mass times gravity times the height, but the height is 0. It's at the bottom. It's it's really, really, really close to the bottom. It's 0.0001 centimeters above the ground. So our potential energy is now 0. Okay, that's interesting. What about our kinetic energy? Well, it has kinetic energy now. We don't know what the kinetic energy is, but we know that the kinetic energy is 1/2 the mass times the velocity squared. Okay, well, if we know the whole system has 1471 joules of energy, and it's not elastic energy and it's not potential energy, that tells us that we must have 1471 0.5 joules of energy at the bottom, and that's kinetic energy. I just need to tidy up this number here a little bit. 71. Okay, so we have that many joules of energy at the bottom. I want to know the velocity. Well, let's see. Velocity would be equal to 2 times the kinetic energy divided by m, and then we take the square root. Okay, and just a little bit of algebra there. I dealt with the 2, dealt with the m, dealt with the square. Okay, so the velocity here would be 2 times 1471.5 joules divided by 5 kilograms. And we're going to take the square root of that. Just for fun, shall I look at the units? Let's do that. Okay, here I know that I've got joules, which is a kilogram, meter squared per second squared, divided by a kilogram. And then we take the square root. Okay. Let's see. So we're going to end up with the kilograms are going to cancel each other. So what I'm left with is the square root of meters squared per second squared. Oh, perfect. That's going to be meters per second. Let me erase that. Equal sign. Okay. Let's get the actual answer now. So 2 times the kinetic energy, so that's going to be around 3,000 divided by 5. It's around the square root of 600. And I have an answer of the velocity is 24.26 meters per second. And I need a direction downwards. Let's try another one. Okay, so here we are. We got a skier. Okay, I'm not much of an artist. on some skis here. There we go. Got some poles. Okay. So this skier's moving this way with a speed of 2 meters per second. And the hill is a vertical hill. I have to be cautious on that. So straight down 45 meters. If it was the angle, then we'd have to find how high, because the potential energy is based on the straight up and down. Okay, and that's 45. The person has a mass of 60 kilograms. All right, and we want to know when she's halfway down. So where's the halfway point? Well, the halfway point is going to be here at about 22.5 meters. So whether it's 22 and a half up or 22 and a half down, whichever way you want to look at it. There's many ways of solving these, okay? I'm going to do it the same way as I did the last one. Elastic energy is 0. The potential energy, let's do that one next. The potential energy is mgh. So we have our mass of 60 kilograms multiplied by our force of gravity, 9.81 meters per second squared, times the height, which is 45 meters high. So we're going to see our potential energy here of 26,489 joules, 26,000, or I could say 26, I could say 26.489 kilojoules. I'm going to leave it in joules, probably a little bit easier. We also this time have a kinetic energy, which is 1/2 mv squared. So that's going to be 1/2 of her mass, which is 60, multiplied by her speed of 2 meters per second squared. That's an easy one we can do in our head. 2 squared is 4. Half of 4 is 2. It's 120 joules of energy. Once again, I can figure out my E total. And this is at the top by adding these together. 0 plus 26,000 plus 120. 120 didn't give us a whole lot of difference. So we have 26,607 joules total energy in the system. How much energy at the halfway? E total at the halfway up the hill. Well, guess what? It's going to be 26,607 joules. Okay. Once again, this is the conservation law. The amount of energy at the top equals the amount of energy at the bottom. Okay. So here we go. Our elastic energy, still 0. But this time we have some potential energy still, because the skier is not at the bottom. Remember, the boulder was at the bottom. So it's now at the bottom, now not at the bottom, halfway at the top. So potential energy is mgh. So mass of 60 kilograms multiplied by gravity, 9.81, multiplied by the height, which is now 22.5 meters high. And what we see is that our potential energy is now 13,243.5 joules. And that should be half of what we had before, right? This was 26,000. It should be half of that because we're halfway down the hill. Okay, our kinetic energy must be the rest. So if we were to take our 26,000 and subtract the elastic energy and the potential energy, we'll get our kinetic energy. So we're going to see that our kinetic energy here is 13,363.5 joules. And we know that the kinetic energy is 1/2 mv squared. And Therefore, once again, 2 times the kinetic energy divided by the mass, take the square root, that is the velocity. So the velocity equals 2 times 13,363.5 square root divided by 60. Skier's velocity halfway down the hill, 21.11 meters per second. Once again, what's the direction? Downward. There is another way to solve these. I realize that. Okay, here's a different question. So we've got a table set up here. Let's put the walls right here, and it's got a spring on the wall. And what we have is we have a cart. It's got a mass of 800 grams, and that cart is moving this way. And what's going to happen is it's going to hit here, and it's going to cause this spring to squish in. And then it's going to come to a stop. Okay? So we know that from here, that this spring is going to condense 6.5 centimeters. And it has a constant of 170 newtons per meter. There we go. Okay. So there we are. We got it all set up. I don't know how fast the cart's going. Once again, we want to know the velocity. Okay. So this time, what do we have? Well, let's see. We have kinetic energy of the cart before. Okay. I don't know what it is. It's 1/2 the mass times the velocity squared. This is what we're trying to figure out. I want to know that velocity. I know the mass, so I need the potential energy to figure it out. Okay. What else do we have going on before? I have 0 elastic energy right now, and I have 0 potential energy. It's not, changing its height as this problem goes on. If this was a slope, if this was going downhill or uphill, then that would be an impact, but it's not. So the potential energy is 0. So I don't know my total energy before. Let's write that as E total. Okay, I don't know that. All right, let's come back. What do I know about the after? Afterwards, well, I still have potential energy of 0. And my kinetic energy is going to be 0. Because what's going to happen is the spring is going to squish until it stops. And when it stops, it has 0 velocity. And with 0 velocity, I'll erase this here. I'm going to, just so I can write that out. It's going to be 1/2 mv squared, but v equals 0. So our kinetic energy is 0. So what we need to figure out here is our elastic energy. Our elastic energy is 1/2 the kx squared. Push this over a little bit. There we go. So it's 1/2 kx squared. Okay, so let's see. So that's going to be equal to 1/2. Our k value was 170 newtons per meter. And we're going to multiply that. Be careful of your units. Get that done correctly. So 0.065 meters. Remember, that's squared. So this is going to give us 0.359 joules. So our total after, our energy total after is 0 plus 0 plus 0.359. So that's our total energy after. Conservation law, that must equal what we had before, 0.359 joules. So now I can use this, because that must be my kinetic energy, because the total was 0 plus 0 plus the kinetic. So the kinetic must be 0.359 joules. And that's 1 half mv squared. And using the same formula as we had before, 2 times the kinetic energy divided by the mass. And we will see that we have a velocity of 0.948 meters per second. And I need a direction, I would say in a positive direction, but in this example, I drew it to the left. If you don't have a diagram, then you can't really explain where it's going. Okay, there was one other thing I just want to point out, is that the cliff problem. Okay, if we have something going to fall off the cliff and it's going to fall down, what if we don't know the mass? Can we still solve it? Okay, and what I want us to look at really carefully here is that the E total at the top, okay, would be equal to the potential energy. Okay, the potential energy, which is m times g times h. The energy total at the bottom is 1 half mv squared. And we know that the energy at the top equals the energy at the bottom. Now, this only works when this object at the top is not already moving. It doesn't have any speed, okay? But what we can see is that the mgh equals the 1 half mv squared. And if I want to know the velocity, I'm going to move some things around. So I'm going to end up with 2 mgh equals mv squared. And then I'm going to move the m over here, and hopefully you're recognizing what's going on. And here's the breakthrough moment. You're going to see that the mass cancels itself out. So the velocity is 2 times gravity times the height. Square root, of course. The mass of the object does not influence how fast it's going when it hits. Okay, so in other words, you could throw, remember, this is assuming that there's no friction, there's no other forces acting on this. But you could throw a golf ball and a ping pong ball off at the same time, and they will be going at the same speed. Now, I will agree, there'd be a little more resistance on one than the other, but it only gets affected by gravity and the height.